today's agenda is the data exploration. We are going to talk about data exploration. What is data exploration in statistics? Basically, the core part of statistics is statistical inference. But moving towards statistical inference and using the advanced techniques from statistical inference, prior to that, one has to explore the data. Try to go through the data and try to find out what does the data try to tell about. The hypothesis testing and conclusions and inference will come later. So this is a kind of pre-inference stage, I would say, as far as statistical analysis is concerned. So we will talk about the different types of variables, then what does the descriptive statistics role in handling any kind of data. Now see, you have to understand one thing, that now we are moving to the statistical analysis. So for statistics as a tool or as a science, it doesn't matter that whether the data is coming from the clinical trials domain or from finance or from any other such area. The statistical techniques remain the same. So that is a very good advantage for statisticians. The techniques remain the same. What is challenging is that whenever you arrive at the conclusions after using those statistical techniques, interpreting them in the language of the user or the person to whom you are consulting as a statistician, that is very challenging. Otherwise, any person having the computer, having the software like SAS, SPSS, StatExact of satellites, many statistical software are there. Anybody can do the data analysis actually, right? Because you can get the data, you can run that software, get the output. What is there? Through the help or the user manual, you can run the software and get the output. But what does the output tell you? So for that, interpreting the output is the main crux of the challenge. So far it is, it's a distant thing for us, at least now, but we will try to approach, always have that thing in our mind, that whatever SAS programs, I am referring to SAS because I know that you are using SAS programs to analyze clinical trial data. So whatever outputs these SAS programs are giving you throughout the clinical trial data analysis, even though you are not from statistics background, you are able to interpret it in a meaningful manner. So that is the objective which I would like to stress again here. So that is the thought behind having this module in the course. Okay, so let us proceed. So all this agenda looks very simple. Statistical reasoning, population and sample, graphical tools. Now bar charts, histograms, pie chart and scatter plots, they are part of any newspaper, any magazine or any website. Even a small kid can interpret these different types of diagrams. So data, types of data. Data is simply defined as the value assigned to a specific observation or measurement. Data is the building blocks of all studies. Parameter, data that is used to describe something of interest about a population. Everybody understands data, so I just read through. What is parameter? Parameter is a quantity which is trying to give rise to that data, I would say. For example, population mean, the mean age of the patient in the clinical trial, or mean, average temperature of a patient whenever he is enrolled in the trial. So that particular thing can be called as a parameter. Then there is a statistic, data that is used for describing a sample from that population. So one key thumb rule I can tell you, that parameters are always meant for populations and statistics are always meant for samples. Now here you will observe that it is mentioned as statistic and not statistics. Statistics is the subject that we are talking about, whereas statistic is a function of the sample observations, and statisticians refer these two differently. So primary data, data that you have collected for your own use, and secondary data, that is data collected by someone else that you are borrowing. But it is not that secondary data is less important than the primary data. It's nothing like that. Everything depends upon the context of the study and interest. Okay. Now where from this variable term has come? This variable is a name given by statisticians to the endpoint which we are referring so far. That endpoint was a response of some treatment, so which you are observing. So here you can consider a variable as any observation or on which you are taking an observation. For example, age, sex, religion, blood group, height, weight, temperature, then cells count, hemoglobin. All these are variables from the statistical analysis point of view. Now, some of them could be the responses in the clinical trial. They could be endpoints. Some of them could be the covariates, which are some other variables you are collecting data upon in the clinical trials data. Okay. So, any variable is classified into qualitative or quantitative kind of variables. The qualitative variables are also called as discrete variables, and the quantitative variables are also known as continuous variables. Discrete variables or the attributes which we call are the classifications into different categories. For example, the severity of some symptom is mild, then medium or high. Then these are three different categories you are talking about. So that variable I will call as a discrete variable, and since it is referring to some kind of order, that is mild, medium and high, so that will go into the ordinal category here, okay, because there is some order. If you are considering a variable like blood group O, A, AB, okay, then the classification is according to nominal, because there isn't any order in that. Okay. The binary variable are the variables which are just classified into this or that. So whether that there is a tumor or there isn't a tumor. Gender is a binary variable. So some such different qualitative variables are there. Then quantitative variables are also called as continuous, are further classified into interval and ratio. The interval variables and ratio variables, there is a subtle difference. We need not worry too much about the difference. Basically, a continuous variable is that you are taking the observations which can come from an interval. For example, height of a person can be 154 centimeter or 154.1 centimeter, 154.799998 centimeters if you are having that accurate instrument. Okay. So this is it's continuous kind of thing. So interval and ratio. What is the basic difference between interval and ratio is that in interval 0 is not well defined. I mean 0 is not defined or it doesn't have any meaning. For example, temperature in centigrade, so and Fahrenheit. So that 0 doesn't mean absence of heat actually. Okay. So it has got some base mark, baseline on which you are measuring that scale. And similarly 30 degrees and 60 degrees, you don't say that the amount of heat present in 60 degrees is exactly the double of that in 30 degrees. So that is interval. Whereas in ratio, you are having that kind of concept that you are having exactly the double amount. We will not hair split the two because we won't come across this kind of classification further. But ratio is the more robust kind of scale, but both are coming from the continuous category. Okay, some examples of quantitative and qualitative variables are like this. Qualitative, now here it has come on the right hand side, the attribute. So gender, severity of pain, race and surgical outcome, whereas the quantitative things are coming as age, then number of patients in a clinical trial, then BMI and number of visits. So they are discrete or continuous. So number of patients in a clinical trial is a discrete variable, whereas age, BMI are continuous variables, number of visits are discrete variable. So the things which you can count are discrete, those are discrete variables. Or you can specify the next number, that is a discrete variable. Okay. Whereas the continuous variables are split into interval ratio, as I mentioned, temperatures in Celsius, years of education, number of publications, and in ratio they can be clubbed as growth of bacterial population, enzyme activity, height, weight, etc. Further classification of the qualitative variables is into the categories of nominal, binary and ordinal. So you have some finite categories, and if they are ordered in some sense, then they become ordinal. If they are not ordered, then they are nominal. So marital status one can consider as nominal, unmarried, married. You may say that unmarried, married, there is an order, but it is generally considered as a nominal variable. Then surgical outcomes, race, European, Asian, American, there need not be any order as such. Something is existing, something exists, something doesn't exist is a binary variable. Severity of pain, stages of cancer, stage 1, 2, 3, 4. Obviously, there is an order due to the progression of the disease, and therefore that particular variable will be considered as ordinal. Then adverse event categories, same as the stages of cancer. Okay, so how does one can look at the statistical analysis? The statistical analysis that you perform on data can be descriptive or inferential. In this descriptive analysis, you just try to understand data. Your approach is not of getting any conclusion out of that data in the descriptive. You are describing data. Describing data means what? See, if you look at a huge amount of data, then you don't come to know anything. But if you describe it in using some statistical measures or in using some statistical graphs, then you get a snapshot of the data. So that is called as describing the data in the descriptive statistics. As against that, in inferential statistics, you are not just satisfied with describing the data. You want to get some inference, some conclusion, because you are conducting a study, you are conducting a clinical trial, and you want to answer a question whether that drug or intervention is effective or not. So this is called as statistical inference. And statistical inference is the main core branch of statistics. One can have series of lectures and courses on statistical inference. Basically, what is done in statistical inference is as follows. In a very crude manner, I can tell you that you take a sample from the population you want to study and you arrive at the conclusion, but that conclusion is not for the sample, that conclusion for the entire population. Here the population doesn't mean the human population. Here the population means the study population you are working on. Okay, so let us try to understand further. So in statistics, if anybody asks you what is the definition of statistics, then it's a collection of methods for collecting, displaying, analyzing and drawing conclusions from the data. So all these go into statistics. And statistical reasoning is based upon the sample. The use of results on a limited sample of patients to infer how treatment should be administered in the general population we will require treatment in the future. So that is what we are aiming at. Now look here, this is a very simple diagram. A sample is shown as a part of the population, and again, which sample, which part of the population, that is very important. So there is a big branch of statistics known as sampling methods or sampling surveys, which talk about how to take a sample, which sample is good, which sample is bad, and all that. So basically, we should have a sample which is representative of the population. If you are trying your drug on cancer patients of a typical type, then obviously your sample should consist of those kind of patients, and they should come from the mix of all the stages of the cancer. If you are targeting all the stages, they should not be only coming from the early stage cancer patients or the late stage cancer patients. So they should be representative of the complete mix of the population. And because of this kind of uncertainty, there are different aspects and research going on how to take a sample. So how to take a sample, which type of sample, how much should be the sample, all these are the questions of statistical interest. So here it's a wonderful slide prepared by my colleague on the population and sample, giving you the idea of what is meant by a sample. So basically, from population, some members are selected in the sample and you call it as a sample drawn randomly from the population. Now here it is shown in the picture, it is a population of people, population of human beings. It may be or it may not be. It can be population of manufactured articles, or for statistics actually it is not the population of people or objects or anything, it is a population of numbers. You are selecting a sample of numbers from a population of numbers which you are measuring. And then, for example, if you look at this particular slide, the question you are trying to ask is that what is the average height of the population? What is the average height of the population? So that average height of population, for example, suppose this is Indian population, all Indians are considered here, then what is an average height of an Indian person? Now in order to answer that question, are you going to measure the heights of all Indians in the census and find out the average of them? Then by the time you compute the average, all of them will be grown up and their heights will be increased. It won't make sense. So, in order to answer such questions, you have to take a sample. So, you take a sample say of 10,000 people, measure their heights, or you might be having that sample available, and then you compute that average height in the sample, and suppose that turns out to be 5 feet. Then that average height of sample, which is called as sample mean, generally denoted by x bar, is known as statistic because it is a function of sample observations. What is its use? Its use is here. So this black arrow is very important. This we say in statistics that this average height in the sample or my sample mean estimates the population mean. I don't know population mean, but because I compute this sample mean, I get some idea about the population mean. Now, if instead of this as Indian population, if this would have been a Japanese population, then my average height in the sample would have been say 4 feet and 7 inches suppose instead of 5 feet. So then you can compare the average Japanese height and average Indian height. So unless you compute these single measures, you won't be able to compare the two huge big data sets. So that is the point actually which we will take it along when we will go in for the next session on measures of central tendency. We will be dwelling upon this population, sample, parameter, statistics all along throughout our course. So you should be knowing the concept, so that's why we included it in our initial slides. Besides this, everybody is aware of these kind of charts. They are bar charts, histograms, box plots, pie charts. These are graphical tools which also describe data, and they describe data in a very effective and attractive manner because just looking at the data you come to know what it wants to tell you. For example, if whatever is this data about, we don't know about it, but still we come to know that if you look at this particular column, fatigue, then people who are having treatment A is having more proportion of patients having fatigue as compared to treatment B. So this kind of comparison you can very well do looking at this particular bar chart. As against that fatigue, you will see exactly the reverse situation with headache, okay, and this kind of thing, this nausea. So you can make certain observations. I won't say that you will make conclusions out of looking at the data. No statistician will make conclusions just as looking at these graphs or charts. But he will record the observations so as that he will proceed further, which is the proper statistical technique. For that, this data exploration is helpful. That which should be the statistical technique I will be using in analyzing the data further. This is an histogram. Now histogram is the frequency diagram What is a frequency? Frequency is the number of observations that belong to that particular class. So here, as it is nothing but the weightage in that class interval. So here you observe that in the initial class intervals, you have very less frequency, then the frequency goes on increasing up to a certain point and then it decreases. So this kind of nature we always come across. For example, imagine that this is a data regarding heights of people. Then if you see the people around you, you will find very few short people and very few tall people. So proportion of short people is very less, proportion of tall people is very less, but the proportion of moderate height is the chunk. Okay, so that's what we observe here. So this kind of phenomenon is observed in almost every walks of life, that this kind of heavy weightage could be shifted this side or that side, that gives us an idea of the skewness in the data. But this is a general tendency that is observed. And when we go to the normal curve, you will come to know that why that normal distribution in statistics is very important. So basically, to a statistician, this kind of data gives an idea that, oh fine, this looks like a symmetric bell-shaped curve, so I can model the data by using the normal distribution. So that is an advantage of these graphical tools. Okay. There is another graphical tool like box plot, which gives you an idea about the spread in the data. Now it is too early for you to understand this, but at least you see that this is a fat box, whereas this is a thin box. So fat box is having more spread, thin is having less spread in the data. So less variation, more variation. So that's what it tries to tell us. Scatter plots tell us about the relationship between two or more variables. You have one variable on one axis, another variable on another axis. Imagine that on x-axis you have height, on y-axis you have weight of a person. Then obviously you see that the data points are likewise this, that as height goes on increasing, the weight also increases. So there is a kind of positive trend in this kind of thing. So this trend, correlation, association, that idea you get from these graphical tools like scatter plots. They are known as scatter plots. Here there is no such trend seen. Here there is a negative trend seen. Okay. So detailed examples we will see later. Here there is a typical observation which is kind of odd person from the rest of the observations, which is known as an outlier. So you get an idea of an outlier also. For example, somebody is typing the data, and instead of 120 mg blood pressure, he typed as a 1200 or 12. Then how will the person who is doing the analysis will come to know that? So just looking at this kind of, you will come to know that there is something wrong with this. So better ignore that, delete that observation, or ask the concerned person whether this kind of observation can be there, and take the steps accordingly. So that is basically the use of data exploration. As a quick check, you can try yourself, think of something and think of some variable which you can measure and try to classify it into the categories that we have learned so far. Height, can it be continuous or discrete? Whether you went to sleep before 11 p.m. yesterday, the answer would be yes or no. It can't be like anything other than that. I went to sleep but I could not sleep, like that. We are not considering that situation here. So it is 0, 1. Month of birth, it can be from 1 to 12. The number of letters in a person's last name can be from 1 or I don't know, from 2 or 1 also. Case of Chinese, maybe. So 1 to say 100 or something like that. Distance from home, educational degree. So you yourself can be, playing this kind of game, think of something and see whether it is an ordinal variable, nominal variable, binary, continuous? Can it be called as ratio variable or interval variable, and so on and so forth? All of you are SAS programmers, and you have seen this kind of reports, or you generate this kind of reports by running procfric or proc summary, proc tabulate, and some such SAS procs. So here you see some of this data like this: race, which is having Hispanic or Latino or not Hispanic, Latino; age, for age you are having these quantities, the number of n is the number of people always, mean, standard deviation, median, quartile 1, quartile 3, minimum, maximum. Age group is classified as below 65 years, above 65 years, or above 75 years, and here you are having the output for that. Could be number as well as percentages, or there are some intervals. So what are these measures and what do they try to tell us? That we will see in our next session, measures of central tendency and measures of dispersion. Okay. I would just like to show you some reports, some output from SAS. See, this was the data, and this is the SAS program that we have used. If you look at the data, you will see here that the variables are treatments, center, multi-center study, patient ID, sex, age, score, response, and severity. All other things are clear. The score is the some kind of a measurement on that disease, and depending upon the score, you are classifying them as no symptoms, mild symptoms, moderate symptoms, and severe symptoms. So basically you are trying to categorize it through using this SAS program, and then you get an output of this frequency diagram or histogram for different treatments, because it is done for treatment A and treatment B by considering subgroups of those patients for these two treatments. So you will see that the frequencies for treatment A for this particular group 10 for mild is higher than that for B. So likewise you can come up with your statements. You can describe it. I mean, one should take up this kind of exercise. Look at the rate chart and describe what you understand from that. Okay. Then this is another done frequency diagram or histogram drawn for severity for the two groups. Then this is a pie diagram, typical pie diagram. Everybody knows that. It gives us the percentage wise breakup of a thing. This is drawn for the severity, I suppose. Yes, pie chart for severity for the entire data, including both the treatments. So you will see that 22%, 22.83% are having zero severity, no symptoms. 33.7 are having severity 1. 15% are having